first thing I'm going to do is a detailed pixel analysis of this picture I took of the Toronto skyline. I've chosen 3 different points of interest along the CN Tower. Each of these points of interest, I know exactly how high they are. I showed you that diagram a little bit earlier. It has all of these elevations in it. So what I'm going to do is I'm going to fill in this chart. Now I've actually already done this, that's why you can see these bars here. But I want to show you how I made those measurements. So here are the real life measurement calculations from the sky pod to the top of the CN Tower, from the edge walk to the top of the CN Tower, and then I need to calculate the horizon to the top of the CN Tower so I can figure out in real life what I'm missing. So I can make that measurement in the picture, and then using the ratios that I come up with, I can figure out my real life measurement. So let's go make those measurements. Sky pod to the top. So I'm going to take the ruler tool and I'm going to measure. This is the sky pod, this little bulge in the middle of the antenna. So I'm going to measure sky pod to the top, and that gives me 543.09. So I'm going to go and record that here, and that's 543.11. It's a tiny bit different than the last time I did it. I think one of my little lines moved. Now let's measure the edge walk. Okay, the edge walk here, which is where you can go and actually go out in the open air and walk along the CN Tower. I'm not sure I could do that now. Maybe 20 years ago I might have been more interested. But we're going to measure from the edge walk up to the top of the CN Tower. And that measurement is 1006.37. So I'm going to go and record that here. 1006.37. That one's dead on. And now we're going to go horizon to the top. So the horizon down here all the way to the top, and that gives me 1995.25. So if I record it here, 1995.26 is what I had the last time. So they're all pretty darn close. Now we're going to set up a ratio to try and calculate the missing in real life measurement. So I'm going to start by comparing the sky pod to the top with the horizon to the top. So the sky pod to the top is 543.11 on the photo, and the horizon to the top is 1995.26. And the sky pod to the top in real life is 106. So we're going to cross multiply this times this divided by this gives us this. 389 meters of the CN Tower are still visible in our picture. So now I want to try, and I'm going to do another ratio measurement. I should get 389 or somewhere around there. I just wanted 2 different spots to work with, just so that I made sure that I'm getting very close to where they actually are. It's a little bit difficult to actually pinpoint exactly where the edge walk is and exactly where the measurement to the sky pod goes. So I thought if I took 2 different measurements, that would probably get me pretty close. So now we want to do the edge walk to the top is 1006.37, and compare that to the horizon to the top, and then we'll do that cross multiply and divide again, and 391. So 384, 391, so it's somewhere around 390. So I'm going to just use the 390 meters are visible. The CN Tower itself is 553 meters tall, so subtracting off the 390 meters that are visible means that there's 163 meters hidden. If you go into Google Earth, it will tell you that around the base of the CN Tower is about 7 meters above Lake Ontario. So the total amount hidden turns into about 170 meters of skyline that is actually hidden. So this is a total summary of my observations. I've put on the actual measurements for each of these key points so that you can see where my in real life numbers came from. And we're going to use these measurements to actually calculate the radius of the Earth. But first, a couple of assumptions that I have made just to simplify the math a little bit. What I'm doing here is I'm assuming that the Earth is a perfect sphere. Now, this is not true. We know it's an oblate spheroid, and it's a little bit wider at the equator than it is from pole to pole. But it's so close to a perfect sphere that it's really not going to make that much of a difference, especially considering that we're rounding numbers to the closest kilometer and things anyway. So it's not going to make that much of a difference. The second assumption is that the distance that I measured in Google Earth, that 53 kilometers from Confederation Park to the CN Tower, that was measured along the curve in Google Earth. We're going to assume that that's the same as the straight line distance. So again, that's not quite true, but the Earth is so large that the distance between those two things is not going to be much different. And when we're rounding to the closest kilometer anyway, that's the difference is going to get lost in the rounding measurements. And lastly, that refractive effects are minimal. They are not accounted for in this analysis. So any error that I might get off of the actual amount could be due in large part to refraction. Okay, now that I know how tall or how much of the CN Tower is hidden, 0.17 kilometers, I'm going to set up this diagram so that we can figure out what the radius of the Earth is. So this is me over here at 0.002 kilometers standing at Confederation Park in Hamilton, Ontario, looking all the way over here, the straight line distance of 53 kilometers to the CN Tower. Now the horizon right here is going to block all of this below, which is the 0.17 kilometers of the CN Tower. And I'm going to split this into two different triangles. Here every radius meets a tangent, and the line of sight is tangent to the circle. Every radius meets a tangent at 90 degrees, so this changes this into two 90-degree triangles, which means that I can use the Pythagorean theorem on both sides. So I'm going to set up the Pythagorean theorem first in triangle ABC. So that would be a squared plus b squared, which in this case is going to be r squared plus x squared, which is down here, r squared plus x squared, and that equals c squared. And c in this side is r plus 0.002 kilometers, so r plus 0.002 kilometers squared. Now I need to expand out this side. Now this squared here means that we have another bracket that's exactly the same, r plus 0.002. And I'm going to use binomial expansion, sometimes called FOIL, to multiply these two brackets out. R times r will give me an r squared. R times 0.002 and 0.002 times r. Those two things are going to give me 0.004. And then that multiplied together is going to give me 0.00004. So once I've got that expanded out, this is what it's going to look like. And that equals r plus x squared. Now I'm going to shuffle this around to try and get r by itself. So I'm going to leave r over here. The two r squareds are going to cancel, so they're completely gone. I can even put a line through them. They don't mean anything to us anymore. So I'm going to get this by itself, which means I have to subtract this off of both sides. So I get x squared minus 0.004, and I'm going to swap sides around here. So that my x squared point minus 0.00004 is over here. And then this is going to be on the other side all by itself. Now to get the r completely by itself, I just have to divide both sides by that 0.004. And I can actually divide these into those two things. So 1 divided by 0.004 and 0.000004 divided by that gives me this, 250x squared minus 0.001. So there's my first value for r. Now I'm going to go over to the second triangle and do the exact same thing with it. So my a squared plus b squared equals c squared. This is going to be my a, this is going to be my b, and then my c this time is r plus 0.17. So what does that look like with Pythagorean theorem? Well, exactly like this. R squared plus 53 minus x squared equals r plus 0.17 squared. Now I'm going to have to expand these out exactly the way I showed you up here, but I'm not going to show that to you again. I'm just going to give you what the expansion looks like and just point out that those r's are gone again. Our squareds are gone because they're the same on both sides, so when I subtract them off, they're gone. Now I want to get r by itself, so this 0.034 I'm going to leave by itself, and I'm going to swap sides again, so it's going to appear over here. And if I'm leaving it by itself and getting everything else here, I have an x squared, I have a minus 1.0 or minus 106x, and then I have to subtract this off of both sides. So 2809 is going to be subtracted by that. And what that ends up giving us is x squared, subtract 106x, and then 2808.9711. And as I did before, I'm going to divide both sides by 0.34, but it doesn't go in nicely like this one did. I'm going to get some really nasty decimals, so I'm just going to leave this here right now. Now, I have two different expressions for r. Since those two r's actually represent the same value, those r's are the radius for all of these things, which is the same number, I can set these two things equal to each other. So this and this are equal to each other, and that's what I'm going to do on the next slide. So there they're set equal to each other, and I want to get x by itself. I want to solve for x. So the first thing I'm going to do is multiply both sides by 0.034. So this side gets multiplied by 0.34, and this side, when it gets multiplied by that, it's gone. Now I need to use the distributive law to expand that into the brackets. And when I do that, I'm going to get 85x squared minus 0.00034. This side remains unchanged for now. And then I'm going to rearrange it all to get 0 on this side. So I have to subtract x squared off of that side, which is going to give me the 84x squared. I'm going to add the 106x on both sides. So it's gone from this side and it's over here. And I'm going to subtract 2808.9771 from this number, which gives me this nasty number. Now this is actually a quadratic equation. A quadratic equation. If I graph it, it's going to look like a parabola, and that's exactly what I'm going to do. I'm going to graph this and try to figure out which values of x is going to make this thing 0. So instead of the 0, I'm going to think of that as being a y, and I'm going to plug it into this fancy-dancy calculator that we have here. This is an online graphing calculator called Desmos, and I'm going to put in this function here. Now I'm not concerned with all of the function. All of this red stuff here, that's all the function. I'm not really concerned with the whole thing. I only care about where it's 0. But I am going to show you what a parabola looks like here. I know this thing has to go way down into the negatives. So I'm going to change my y to start at negative 3,000. So that you can actually see that it's a parabola here. And the only 2 points I'm concerned with are this one and this one. Those are the two things that x can be in order to make this 0. Now this one is negative, and since we're talking about a distance, we don't want a negative value. So I'm going to ignore this number, and this is our value. So Desmos gave us these two values for distance to the horizon. A negative distance to the horizon doesn't make any sense, so we're going to ignore that one entirely. So what this tells us is the horizon is 5.186 kilometers away. Now we didn't want the distance to the horizon. We actually wanted the radius of the Earth. But remember, we had those expressions for radius. Here's one of them. It used to say r equals 250 x squared minus 0.001. Well, now that we know what x is, we can plug it in, and this is what we get for the radius of the Earth, 6,724 kilometers. Now, the known value for the radius of the Earth is 6,357 kilometers, so we got pretty close. In fact, it's only 5.8% off. So I repeated this whole process with my second photo that I took from the top of the escarpment. Now, at the top of the escarpment, I was considerably higher, so there wasn't a whole lot, even though I was farther away as well. This time I was 59 kilometers away, but I was 106 meters above the ground at the top of the escarpment. So there was only 38 meters missing, and as you can see, you can even see a large portion of the Rogers Center there. So I still calculated that there were 38 meters missing, and I went through this whole process again. Now I'm not going to go through this in as much detail as I did the last one. I'm just going to scroll through it quickly, and I will put a link to my entire paper that I put together on this in the doobly-doo below, so you can have a closer look at it if you want to. So here's the second picture. Now I have a little note up at the top. The second photograph was taken from the top of the escarpment, analyzed in the same manner. As expected, more of the skyline was visible from the top of the escarpment. It's also expected that refractive effects won't play as big of a role in what we see from a higher elevation, thus giving the radius of the Earth closer to the geometric radius than the analysis from the beach. So that's what is expected with what we know about refraction. Let's see how that panned out. So you can see I've changed the diagram slightly. This is a little bit higher. And so we can see we go through the entire process, same as before. And what I end up finding is that the distance to the horizon, using all of the same things, is that it's now 36.9 kilometers to the horizon. So the horizon got pushed back quite a bit by me going up higher. And then we plug it back in, and what I got for the radius of the Earth this time was 6,424 kilometers, which is actually really close to the accepted value of 6,357. In fact, it's only 1.1% difference. So refraction wasn't really playing a big part in what I saw from the top of the escarpment. Now, just a couple words on where error might have come up. I was rounding. So I rounded to the closest kilometer for the distance away. I rounded to the closest meter for how much was hidden. So the rounding could cause us a little bit of error. Incorrect measurement, so I may not have got exactly the guide set right and had some of the pixels. And the biggest cause for error would be the refraction. So because refraction does play a large role in what we see across water, I did minimize the refractive effects by viewing the Toronto skyline on a day when the water temperature was very much the same as the air temperature, and so there wasn't very much refraction actually going on.